So you're going back to graduate school, but it's been a little while since you've seen the type of math tested on the GRE. Well, fear not, because that's why I'm here, and that's the purpose of this video, to teach you the three most important mindsets and tangible strategies that will put you in the best position for success on test day. In essence, to teach you how to dominate the GRE. Hi, my name is Brett Etheridge, founder of Dominate the GRE, and for over a decade now, we've been equipping and empowering students just like you from all around the world to dramatically increase their GRE scores and get into the graduate programs of their choice. Now, I want to dive in. We're going to get very concrete, very tangible, get a piece of paper, kind of some notes, get ready to take some notes. We're going to work a few problems together, but I want to start by actually commending you, by applauding you for taking this next step. You know, I know most of you watching this video are over 30, and don't worry if you're under 30, everything that I talk about in this video will help you and will apply to you as well on test day, but you're making a shift in your career. And I think that's awesome. One of my favorite quotes is that it's never too late to be who you might have been. You know, I believe that we all have kind of God-given talents that we need to employ, and we don't always figure out really what we're supposed to be doing and kind of our ideal calling until later in life sometimes. And so that's awesome that you're in a position where you're ready to either kind of move up in your current career or maybe shift laterally, maybe kind of move careers altogether. I had a gentleman a couple of weeks ago actually call me in his 70s, and he's looking to go back and get a PhD in biochemistry or genetics or something like that. He's worked in genetics for his whole life, and I just think that's absolutely awesome. So wherever you are, and then in fact, leave a comment below. I'd love to kind of know where you are and why you're making that transition, and maybe you're in your 40s, maybe in your 50s, looking to make that move. And so congratulations on that. That's very, very exciting. But let's address kind of the big pink elephant in the room, which is that you're kind of pretty far removed maybe from your high school days, certainly. And it's been a while since you've been in school. It's been a while since you've had to study the type of stuff that you're going to see on the GRE. So what do we do? How do we get there? And that is the purpose of this video. Like I said, we're going to go through three mindsets. We're going to get very concrete and work a few problems together. Let me give you the good news first as an over 30 test taker. When you think about the entire application process for graduate school, you actually have a lot of things working in your favor. Right? You're a well-rounded candidate. You have some work experience under your belt. You're going to bring a lot more to the table in terms of your overall application than a lot of your peers and a lot of the people that you will be competing against during the application process. So that is awesome. And when it comes specifically to the GRE, right? There are two sections, the quant section and the verbal section. Let's talk about demographics for a second, right? I've seen these numbers broken down by age group, right? So there are groups of people taking the GRE who are in their early 20s, right? Pretty close still to their high school days where they learned all of the type of math tested on the GRE. And then there's kind of the middle group, and then there's the over 30 test takers. And let me ask you this question. Who do you think does better on the verbal side of the GRE? The 20-somethings, the early 20-somethings, even 18 to 19-year-olds are included in the demographics of people taking the GRE, or the over 30 group? And the answer is you guys. The over 30 demographic actually statistically does better on average than anybody else on the GRE. And it's probably because you've had more time to read, you've improved your vocabulary a little bit just as you've gotten older and wiser and read more. And that's not always the case, but you had that working in your favor. And so it's not to say that there aren't things you need to learn, vocabulary you need to study, things that we can teach you. But in this video, we're going to focus on the quant section. Because when you look at the same demographics, who do you think does better at quant? Yeah, it's the younger group. In fact, the very youngest demographic has the best average quantitative scores. And again, I think it's just because it's freshest in their mind since they've done right triangles and quadratic equations and all the stuff that you learned back in high school. And now for you maybe watching this video, it's been a little while. So good news and bad news. And like I said, we're going to dive in. Let's take a look at those three things. Heavy emphasis on quant, but now I think you know why. And here we go. So without further ado, mindset, strategy, whatever you want to call it, number one for maximizing your success to dominate the GRE is to just know that everything on the GRE is learnable, or in some cases, relearnable. Now that should be encouraging to you to know that everything you're going to see on test day not only is not going to be a surprise, we know everything that's on the test, but that it is learnable. Now you might be thinking to yourself, you know, I wasn't even very good at math when I was in high school. So forget the fact that it's been a while. I wasn't even really good at it back then. Am I a hopeless case? I get emails from prospective students like that all the time. They say, here's my situation. I've been out of school a really long time and I was terrible at algebra anyway. Is there any hope for me? And my answer to you is yes, there is hope for you. But I want you to adopt this mindset. The way that you want to learn the underlying content on the GRE is a little bit different than you may have learned it back in high school. And that should also be encouraging to you because your goal on test day is not to make your high school algebra teacher proud, right? You don't have to show your work, hey, here's how I solved for X. Your job is to get right answers. And so you want to study the content with an eye towards getting right answers. You want to learn strategies for getting right answers more efficiently. Hint, hint, kind of tactic number two, strategy number two that we're going to talk about here. And you want to learn things in a slightly new way. I get comments all the time from students saying, man, I wish you had been my high school algebra teacher because you teach me how to attack question types in a way that just makes more sense to me. So everything is learnable. You want to learn it in the ideal way to get right answers. And let me prove it to you that everything is learnable. Take a look at this example. So here you go, question number one. And it reads that in the figure below, the square has two sides that are tangent to the circle. If the area of the circle is 4a squared pi, what is the area of the square? And then you have your answer choices, and we're trying to find the area of a square. Now I know for some of you it might have been a really long time since you've seen something like this. For others of you, you actually are going to do okay with this and get the answer pretty quickly. Even if that's you, kind of hold tight because I'm going to show you some shortcuts and some ways of solving this problem more efficiently. But for all of you, go ahead and just take a few minutes, try to do it on your own, and then we're going to come back and do it together. So go ahead and press pause and try it on your own. Okay, so how did you do? Well, like I said, everything is learnable, and you might be thinking that, I don't know. Everything with this problem can be solved by learning just three things, or being reminded of just three things. So what I'm going to do is I'm going to take you through a very traditional approach to solving this question, again, just to prove to you that everything is learnable. And then we'll turn to kind of point number two, where I'm going to show you how to do it in a little bit more easy way. But what are the three things that you need to know? The first is the area formula for a circle and for a square. So just by way of reminder, we're told that the area of a circle, is 4a squared pi. Well, the generic formula for the area of a circle is pi r squared. So that might be bringing some big things back to you. Pi r squared is the area of a circle. The second area formula that you need to know is that the area of a square is the side, so we'll just call that S. A square, of course, has four sides that are the same. So the area of a square in red here is the side squared, which again is just the side times the side. Right? Because the area of a rectangle or a quadrilateral is the base times the height, but here the base and height, since it's a square, are the same, so we can just think of that as side times side, base times height, which are the same thing, which is the same thing as side squared. So there you go. We're told that the area of the circle is 4a squared pi, and we simply need to figure out what the area is. So there we go. Literally, I know the answer as soon as I know what S is. As soon as I know what the side of the square is, I have the answer to the question. So now how do we get there. Well, that kind of brings us to the second thing we need to know, which is a little bit about square roots and squares, because let's go ahead and solve for the side. Now, the other thing to recognize with this problem, of course, is that the side is the same thing, right? The side right here is the same thing as the diameter of the circle, right? Because it is tangent. Because it is tangent, that means it touches at exactly one point. That means that the side would cut right through the middle of the circle. So the side is the diameter of the circle, which the diameter, d, equals twice the radius. So remember, the radius of a circle is the line segment that radiates out from the center of the circle towards the circumference. So r, the radius r, is just kind of half of the whole diameter. So that's kind of another thing to know. And now that we know that, if we can use the area formula to find the radius, we can just double the radius to find the diameter, and then we can solve for the area of the square. So that's kind of how this works. Let's go ahead and do it. Again, we're told up here that the area is 4a squared pi. We know that equals the formula for the circle, pi r squared. And so let's go ahead and solve this. If pi r squared equals 4a squared pi, well, the pi's are common to each side, so we can kind of like divide out the pi from both sides. So now we have a situation where r squared equals 4a squared. So the radius is therefore just the square root, right? R squared, you would take the square root of both sides. So the radius is now the square root of 4a squared. And this is where I said one other thing to learn that you might not have seen for a while is how squares and square roots work. Again, all things that you can learn, but if you're not quite sure what to do with that, you can actually break out the stuff underneath the radical, underneath the square root sign, and say, okay, that's the same thing as the square root of 4 times the square root of a squared, okay? And that is going to equal, that's a little bit easy, right? The square root of 4, a square root is just whatever the square root is when that thing's multiplied by itself would equal 4. So the square root of 4 is just 2 because 2 times 2 is 4. So we have 2. And then the square root of a squared, it just kind of negates the square term, so it's just a. So 2a. So the radius is 2a. So there you go. Radius is 2a. And then what did we already decide? We decided that once we knew the radius, we now know the diameter, because the diameter is twice the radius, 2a, or 4a. So the diameter, the whole diameter, is now 4a, which means all of the sides are 4a. And then we already realized up here that the area that we're looking for is the area of the squared, which is the side 4a squared. So that's 4a times 4a. And the way that works is you multiply the coefficients. 4 times 4 is 16. You multiply the a's. A times a is a squared. So we have 16a squared. Answer choice D. You check it and you move on. Now, is that painful or not? Right? That wasn't too bad. You just learned something, hopefully. Hopefully some things that you had forgotten from all those years ago. Light bulbs are coming back on. Oh yeah, area of a circle, you know, diameters, radiuses, taking square roots, radii, taking square roots, taking squaring things, right? And it doesn't mean that you're not going to have to brush up on this a little bit more. It's not like you don't have to dive a little bit deeper than what we just did here, but hopefully you at least now realize, okay, I can learn this stuff. I can do this. Look at that. I at least understood what he was saying. I can get a right answer. Now, here's the cool thing, which brings me to point number 2. If you are going to put yourself in the best position for success on the GRE, especially if it's been a while since you've been in school, learn to do problems like this without actually doing it this way. So wait a second, Brett, I just watched this video for like 10 minutes. You just walked me through all this stuff and you don't even want me to solve it this way? I was simply showing you that you can learn it. But now let me show you how to get a right answer on a question like this a lot faster, a lot more efficiently. And in fact, that brings us to my point number 2, mindset number 2, strategy number 2 for succeeding on the GRE as an over 30 test taker is to learn to do things in a non-traditional way. That's right. Mindset number 2 is to use non-traditional math strategies whenever possible. So let's actually look at this exact same problem a second time with this in mind. And what I want to do is I want to teach you how to get a right answer on this question in a different way, in a non-traditional way that I think you're going to think is even better and even more efficient. So how would you get a right answer on this question in a different way, in a non-traditional way, without going through kind of the steps I just did and literally solving for, the radius and extrapolating that to the diameter and actually solving the problem? Because here's the other thing to remember on the GRE. The GRE is actually a reasoning test. Despite the way it kind of looks, it's not necessarily just a math test or a vocabulary test. It's a reasoning test. And there will be times on test day when a question will pop up onto your screen, no matter how well you've prepared. Maybe you've taken my course and you've learned a whole lot, and yet there still might be a question that pops up and you just don't immediately know how to do it. So what do? You panic, you freak out, you guess, you skip, you take 10 minutes trying to solve this one problem and mess up all your time management. Or do you try to think, okay, take a deep step back, take a deep breath, and let's see if we can reason our way through and still get a right answer, even if we didn't know how to immediately do the math. Put another way, is there a way we can come at this problem in a non-traditional way and still get a right answer? Because that's your objective. And again, as we talk about, as an over 30 test taker, putting you in the best position to do well on the GRE, that's going to require you to get right answers, sometimes against all odds. So imagine this question popped up on your screen. You didn't immediately remember or know how to do the traditional math. How could we still get a right answer? There are 2 answers to that question, 2 different kind of approaches, 2 different mindsets. I'm going to talk about them both here. And the first would be, let's guesstimate, let's eyeball. If you have a figure on the GRE, now figures aren't necessarily drawn to scale, right? Especially on quantitative comparisons. We're going to talk about that here in a second. They're almost never drawn to scale, and so you can manipulate the diagrams. But on problem-solving questions, all we're told is that we have this square and that it's tangent. That means it touches at exactly 1 point. But it's drawn to scale, so how can we use that to our advantage, right? Well, we're told this area. Now what if, again, using reasoning, a little bit of creativity, you think, well, if this area right here, I'm going to change pens here a second. If this circle has an area of this, like whatever that is, it contains pi's and a's and stuff like that. Like what if we kind of mentally shift this circle like over, right? So that it were right in the middle of that square. Let's pretend this thing fit inside that square. And you might be thinking, Brett, you can't do that. That's not the way the figure's drawn. Well, all I'm doing is comparing areas, right? That circle could just as easily have been moved to the right a little bit. Now it's inside that big green square. And now visually, I can literally see the difference, right? If this big area is 4a squared pi, like whatever that is, the square is just a little bit bigger than that, right? In fact, it's bigger by essentially this shaded area. You see that? So I hope light bulbs are starting to come on, like, oh, I can like cheat on the GRE? Yes, you can cheat. It's not cheating, you're just using reasoning. I'm teaching you how to apply strategy and logic and non-traditional approaches. So if this circle is 4a squared pi, the square is going to be a little bit bigger than that. Okay, well, which of the answer choices is a little bit bigger than that? Well, you can just kind of visually look and see, like, 4 is the same thing. 16 and 64, these are going to be bigger. And in fact, here's another thing to remember, right? You have your calculator on test day. What do we think about pi as? Pi is approximately 3.14, right? Pi is just a number. So another way to think about it is pi times 4, 4 times 3.14 is about 12.5. So it's about 12.5 a squared would be another way to think about the area of the circle, 12.5 a squared. So we know that the area of the square is going to be a little bit bigger than that. So if this is 12.5 a squared, 4a squared is a whole lot less than 12.5. That's wrong. 4 is not only less than that, we're not even squaring the a here, so that's smaller. That's smaller. At worst, you now have a 50-50 guess. And at best, you'd realize, okay, the square is bigger than the circle, but not that much bigger. Not like 4 times as much, almost 5 times as much. So you would get the right answer anyway without doing any math, just by using the figure to your advantage, using a little bit of reasoning. Now, a second approach to this would be, that absolutely works. A second approach to this would be a strategy I use that's called making up numbers, right? So there are two really, really useful non-standard strategies, non-standard math strategies. One is to work backwards from the answer choices. I'm not going to go through an example of that here in this video, just in the interest of time, but definitely learn that strategy, which is basically to work backwards from the answer choices. When you have multiple choice answers, you can actually say, okay, I don't know, one of those 5 answers is correct. Let's kind of plug it back in. Let's work backwards and see which one actually works. It's basically just like testing the answer choices to see which one works. It's a great strategy, right? You don't always have to make your high school algebra teacher happy, right? I've already said that once, but I want you to adopt that mindset. Your job is to get right answers. You don't always have to solve for X. That doesn't work here because we have variables in the answer choices as well. So what's the strategy here? The strategy here is, this problem is annoying because we have variables in it. Well, what if we take variables out of the equation by making up a number for that variable? In other words, A is some like abstract algebra thing that doesn't stand for anything. It's annoying to work in the world of A's. So what if we just say A equals 3? Brett, you can't do that. Sure, you're just making up a number, right? A can stand for anything. What if A equals 3? Well, now the area of the circle is 4a, but a is now 3 in my world, 3 squared pi. 3 squared is 9, so 4 times 9 pi. 9 times 4 is 36 pi, right? So the area is 36 pi, right? The problem just as easily could have told us that the area is 36 pi. Well, in our world it now is, because I'm letting a equal 3. Okay, so if a equals 3, then the area is 36 pi. We do need to remember that the area of a circle is pi r squared. So that means that pi r squared now equals 36 pi. Hey, look, now we're working with a real number. The pi's cancel, so r squared equals 36, so r equals 6. That's a lot easier, right? We recognize that the radius is half of the diameter, which means, the whole side of the square is going to be twice the radius, or 12. So now we have a real number we can work with. Let's go back to the green pen color. So now the side of the square we know is 12. We do need to remember that the area of a square is the side squared, which is now 12 squared, which is 144. So what happens with this strategy is, we make up a number for the variable, and then we literally solve the problem using our made-up number. So in a world where a equals 3, which is a perfectly allowable value for a could stand for anything in this problem, the actual answer to the question is 144, right? That's the answer. And now we have to check the answer choices, and you say, yeah, but those answer choices, none of them look like 144. They still have like a's in them. Well, let's take our same a equals 3 and plug 3 in to all of the answer choices, right? So answer choice A, 3 squared is 9, 9 times 2 is 18. Nope, that doesn't equal 44. That's not right, right? 4 times A is just 4 times 3 is 12. Nope, that's not, right? And so you just work your way down until we already know the correct answer. The correct answer is 16. A squared, 3 squared is 9, so 16 times 9, what does that equal? You can use your calculator if you need to, but that's 144. Hey, look at that. It's the same thing it's supposed to be. I just solved for the area of the square, 144, and it matches. So that's another brilliant strategy that will serve you well, especially on questions, problem-solving questions that involve variables. So I hope light bulbs are going on. Go ahead and leave a comment below. We'd love to hear from you. Hopefully you like this strategy if you haven't seen it before. But again, as you're thinking about putting yourself in the best position for success, non-traditional approaches are great. Either using a little bit of reasoning, a little bit of logic, using the figure to your advantage, and frankly, just flat out eyeballing the right answer, as we did first, or following the steps of this non-standard strategy of saying, let's take ourselves out of the hard world of algebra where I have to solve something, and instead just work with real numbers and see how that plays out. And so that's your strategy there as well. So tip number 1 for you, realize that everything is learnable. Learn it, especially in a way towards putting you in a position to get right answers. Part of that is number 2 is use non-traditional strategies on the math section whenever possible. And the final point that I want to talk to you about in terms of a mindset and actually a strategy applies to quantitative comparison questions. Remember that there are 2 major question types on the quant section of the GRE. One is problem-solving questions like you see here. There's also a data interpretation questions with tables and graphs and charts and things. But kind of run-of-the-mill math questions, and then a unique question type to the GRE called quantitative comparisons. And so my third tip for you, my third point, applies to these subset of questions called quantitative comparisons. And the strategy, the mindset here is compare, don't calculate. Take a look at this example. Now, for some of you, you might be seeing quantitative comparisons for the first time. As I mentioned, they are a unique and a little bit weird question type until you get used to them, and then they'll eventually get to the point where you'll wish there were more of them on test day, especially if you learn the correct methodology for them. But basically, you're comparing 2 quantities. Quantity A on the left compared to quantity B on the right. And in quantity A, we're told that, or asked to find the sum of the even numbers from 2 to 100 inclusive. And the question is that more or less than 52 times 50. And if you're not familiar with the answer choices, you can see them listed below. There are ways to interpret those. My goal here isn't to teach you how to do quantitative comparisons, but more to teach you, again, the mindset that you want to take toward quantitative comparisons. So if you want to try this on your own, go ahead and press pause, give it a try, and then we're going to come back and I'm going to show you a few important ways to think about a problem like this. Go ahead and press pause. All right, so how did you do and how did you conceptualize this problem? Well, I already gave you the hint, and the mindset you want to carry to quantitative comparisons is compare, don't calculate. And I think once that kind of light bulb goes on, that's a big part of having more success on these question types. What they don't want you to do is literally add up all of the even numbers from 2 to 100, right? And so hopefully that's not what you did. Even if you have a calculator, you only have, a minute and a half to a minute 45 per question on average. And so you don't want to spend your whole time punching in 2 plus 4 plus 6 plus 8, right? All the way up. So how do you think about this in a slightly different way? Compare, don't calculate. Likewise, I'm not even going to bother typing in 52 times 50 on the right. Yeah, maybe that'd be helpful to know what that is, but I want to compare these 2 terms, right? So how do we think about that? And there are a couple of ways of conceptualizing this. The first is to recognize, well, a great place to start would be to say, okay, how many of those numbers are there even going to be, right? 2 plus 4 plus 6 plus 8, plus blah, 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 plus 48 plus 50 plus 52 plus 54, right? All the way up to plus, 96, 98, and 100 because it says inclusive, right? So how many of those numbers are there? Well, If you were going from 1 to 100, how many would there be? There would be 100 of those numbers, right? And we're essentially just cutting that in half because we're only doing the even numbers. So half of that is 50, right? There will be 50 such numbers. That must be where they're getting something times 50. So over here, we're going to have something, right? Something times 50, because there are 50 such numbers. See how the thought process works? So really, I'm just comparing to like whatever this thing is times 52. So what would that number be? What am I multiplying by 50? Well, what I would be multiplying by 50 would be the average of all those terms, right? The average of all those terms. Let me give you a quick example. Let's say you were trying to find the sum of 2 plus 4 plus 6, right? What's the average of that? Well, obviously I could just add them up and divide by 3. Or I could say, you know what? 2 is the same amount less than 4, that 6 is the same amount more than 4. So really, it's like we have 3 4s, like 3 times 4, right? Sorry, not finding the average, finding the sum. Finding the average would be adding those up and dividing, right? So what's the sum of 2 plus 4 plus 6? Well, again, that would be easy to do on your calculator, or you can conceptualize it as, well, it's really like I have 3 4s. That's going to be the same thing as 4 plus 4 plus 4. Because again, 2 is 2 less than 4, but 6 is 2 more than 4, so it's really like I have 3 4s. In other words, if I'm finding a sum like this, it's just whatever the average is, and the average of those numbers would be 4. The average is 4 times however many terms there are. We teach that in weighted averages. It's essentially just a weighted average. Not my purpose here to teach you that, but simply to get you thinking about, okay, so if that's essentially what's going on, I have 50 numbers that average to what? And that's kind of the next question. The next question is, what do they average to? Well, the beautiful thing about math, when you have the sequential numbers, even though they're all even, they're evenly spaced, the average would just be the middle number. Just like if I were adding 1 plus 2 plus 3 plus 4 plus 5, the average will literally be the middle number, right? As long as they're evenly spaced. But what happens if we don't have an odd number of terms, which we don't have here, right? We have 50 terms, so that's an even number of terms. So that'd be like if we had 1 plus 2 plus 3 plus 4. We have an even number of terms. What's the average of those? Well, it's still the middle term. The middle term, but we don't really have a middle term. The middle term is just the average of those two middle numbers. So the average of 2 and 3 would be 2.5, right? Up here it would be the exact same thing. The average of all 50 of those terms would be the middle number, but we have an even number of those terms, so the average would be the average of the two middle terms, 50 and 52, which would average to 51. So we have 51 times 50, and so literally we have the 50s in common. We're literally just comparing 50 to 52. And which is bigger? Compare, don't calculate. 52 is obviously bigger than 51, so that product will be bigger than this sum, only by a little bit. A lot of people might have looked at that and said, I'm multiplying two things together. That's probably going to get a lot bigger than if I'm just adding a bunch of stuff together. Be careful with that thinking, right? There's no logical justification for that necessarily. That product, 52 times 50, won't be very much bigger than that sum, but it will by just a little bit, because 52 times 51 is a little bit bigger than 51 times 50. So the correct answer would be answer choice B, right? Compare, don't calculate, right? Overriding concept. Now, there are certainly more things to teach you with respect to quantitative comparisons, some question types that involve variables. Hint, hint, you'll make up numbers when you see variables on quantitative comparison questions. So there are definitely some other strategies that you'll want to learn in terms of quantitative comparisons. But I think as you venture into the world of the GRE, and you're looking for that edge, especially as an over 30 test taker, as somebody who hasn't seen this stuff for a little while, I hope now you're starting to understand the thinking that you want to bring to the GRE if you're going to put yourself in the best position to dominate the GRE.